To start out with simple harmonic motion, the first thing we want to talk about is Hooke's law. Hooke's law has to do with something called a restoring force. So let's picture this situation. We take a mass and we attach it to a spring here. Okay, and then we take this spring, we take this mass and we stretch it out to here, and then we let go, and what happens is it's going to move back and forth around sort of this center position that we're going to call our equilibrium, or x equals 0. Okay, so it's going to move back and forth here, some distance back and forth, and the further we get away from 0, the harder our spring is going to pull back, and the further we get away this way, the harder it's going to pull back. That pull back towards equilibrium is what we call the restoring force. And that restoring force is proportional to this distance that we are from equilibrium. So that restoring force is equal to negative kx. Okay? The negative here comes from the fact that it's always pulling backwards against the object's motion. X is our displacement, how far away we are from this equilibrium point. And k here, though we might not have used it in a while, is something we should be familiar with. And that is our spring constant for the spring. Okay, so our spring constant for the spring, how strong our spring is, times how far away we are from our center point, gives us our restoring force. So let's just look real quickly at a spring moving back and forth. Okay, we can see our force pulling back here. Here we're at our equilibrium point, and our force moving forward here. Just a couple important things to point out here. First, when we're at our very ends here, okay, this is the point where we're turning around. And so you can kind of compare this to like when we were throwing a ball up in the air. At the point where we were turning around, our velocity was equal to 0. So our velocity is going to equal 0 at these endpoints. However, on an interesting side note here, because the force is proportional to the distance away that we are, and here we're at our maximum distance away, so maximum force also gives us our maximum acceleration. So at the points where we're turning around is where our acceleration is the greatest, because that's the point where we have the greatest force. Here, when we're at equilibrium, because there's 0 displacement, there's 0 force, so my acceleration is going to be 0. But because I'm not being pulled back in either direction, I'm not being slowed down at all, my velocity is at its max right in the center of its swing. And that's going to be a feature of any simple harmonic motion, whether it's springs going back and forth or even a pendulum swinging back and forth. Anything that's simple harmonic motion is going to kind of have those characteristics to it, where in the center its velocity is at the max, and at the edges is where it's going to have its maximum acceleration. A couple other important characteristics of simple harmonic motion are period and frequency. Period is the time it takes to complete one cycle of motion in simple harmonic motion. Okay. And frequency is the number of cycles completed per second of motion. So period, the amount of time it takes to complete one cycle of motion, and frequency is the number of cycles completed per second. So we can kind of see from our definitions here that these things are inverse of each other. Period, okay, we usually use the capital T as our variable, and for frequency it is a lowercase f. And since they are inverse of each other, we could say that period equals 1 over frequency, or frequency equals 1 over period. So you can determine one from the other as long as you know what it is. Period is usually measured in seconds. So if we look at frequency, 1 over period would give me 1 over seconds, which is equivalent to a unit we call hertz. So frequency is measured in hertz, which is a unit of 1 over seconds, right? Cycles per second maybe is a good way to think of frequency. So a quick sample problem here. An ultrasound machine uses vibrations with a period of 0.6 microseconds to create an image. So we have a period, t, equals 0.600 microseconds. So remember, that's our abbreviation for microseconds. We want to know, what is the frequency of the ultrasound machine? Okay. Well, we have our relationship there that frequency is 1 over period. The only thing we have to be careful of is our units, right? 1 is easy, but we have microseconds here. So remember, micro means times 10 to the minus 6. So we'd say 0.600 times 10 to the negative 6th seconds, so that's in units of seconds. If we put that into our calculator, we get about 1.7 times 10 to the 6th hertz. Okay. So that means the sound in an ultrasound machine that is used to create the image is vibrating back and forth at 1.7 times 10 to the 6th hertz, or 1.7 million cycles every second. So now let's really get into simple harmonic motion. Simple harmonic motion is any motion that follows Hooke's law. So any motion in which that restoring force is proportional to how far away you are from equilibrium falls under the category of simple harmonic motion. When we talk about that displacement from equilibrium, another important point is amplitude. Okay, amplitude is our greatest distance from equilibrium. Okay. And one kind of important feature of simple harmonic motion is that our period and frequency have nothing to do with amplitude. They're independent of our amplitude. So how far away you go doesn't affect how fast it's moving back and forth. When it comes to a system that we talked about where we have maybe a mass attached to a spring and it's moving back and forth, which is kind of a common situation for us. Turns out the only two things that affect period and frequency are the mass of the object attached to it and the spring constant. Okay, if we have a spring constant that's big, then it's going to move back and forth really fast because we have a really stiff spring. If we have a mass here that's really large, it's going to move back and forth really slow because it's going to have a low acceleration because of that big mass. It's going to have a lot of inertia, not want to change direction very quickly. So we've come up with an equation where we can calculate the period of this kind of simple harmonic oscillator of a mass spring system. So for a mass spring system, the period equals 2 pi square root of m over k. And in here, m, of course, is mass, and k is our spring constant. So just like we said, it only depends on mass and spring constant. For frequency, remember that frequency is equal to 1 over period. So if we just take the inverse of what we just wrote there, we could calculate frequency by saying 1 over 2 pi equals the square root of k over m. So just kind of flipping everything around, we can calculate the frequency and get it in hertz. So in these equations, your period here is going to come out in seconds. Frequency will come out in hertz. Waves, it turns out, are another form of simple harmonic motion. So let's again kind of consider our spring here, and this time we're going to do a spring that's maybe vertical. And then we're going to attach our mass to the end, and then it's going to move back and forth, right? We're going to take our hand and pull down on it, and then let it go, and it's going to bounce up and down. And as it bounces up and down, let's create a graph here of time and displacement x. Well, as this happens, right, it's going to start to move very quickly, but start to slow down as it gets near the end, and then turn around and come back the other way, and speed up and speed up and speed up, and then until it gets to the end, slow down, and this is what its motion would look like. Well, that looks like a wave. So simple harmonic motion can also be described as a wave. In fact, waves are a type of simple harmonic motion. If we talk about sound waves, earthquake waves, light waves, whatever, they are a type of simple harmonic motion. And you can kind of see the similarities between something where we can talk about and visualize real easily and a wave itself. So there are ways you could even use wave equations, things like sine and cosine, to describe their motion. We won't get into those in this class, but you can see the relationship there.